Hello, everybody. Today we are going to be taking notes on states of matter. We kind of sort of started talking about it yesterday, but you're going to be taking your PowerPoint notes on it today. So go ahead and get out those PowerPoint notes. They should be fill in the blank notes like you've seen before. All right, so we'll start by talking about the kinetic molecular theory. Kinetic molecular theory is the idea that all particles in all states of matter are in constant motion. How quickly those particles are moving depends what state of matter that substance is in. Temperature, then, is the average kinetic energy of those particles in motion in those different states of matter. Okay, so we're going to talk about the three different states of matter next: solid, liquid, and gas. All right, so the three pictures you see on the screen here, the one all the way on the left is kind of a picture of solid particles. They kind of just vibrate in place. Liquid particles flow past one another, and then gas particles are spaced really far apart and moving really quickly, bouncing off the walls of their container. Okay, so what I will show you next are kind of basic definitions of each phase of matter. Solids have a definite shape, and they do not take the shape of their container. So when you put a solid into a container, it doesn't change its shape to mold to the shape of that container, whereas a liquid and a gas both do take the shape of their container. Okay. Solids also have attractive forces that hold all those little particles together in a fixed position. That's why their shape stays the same. Liquids, like I just mentioned, do take the shape of their container, but they do have a definite volume. So what that means is if you have 20 milliliters of water in a graduated cylinder and you pour that into a beaker, it's going to take a different shape. It'll take the shape of whatever container it's in, but it stays that 20 milliliters of water. It has a definite volume. Gases have neither definite shape nor definite volume. So gases will expand or contract to fit the shape that they're in. And because they can expand or contract to fit the shape that they're in, they also don't have a definite volume because they can either be compressed or expand depending on the container that they're in. All right, characteristics of each. So characteristics of a solid, they have a definite shape and volume, a definite melting point. What that means is that if you have solid ice, no matter how much ice you have, it will melt at the same melting point. They have a high density because all those particles are packed in really closely together. They are incompressible. What that means is it's very difficult to compress a solid because the particles are already close together. And they have a low rate of diffusion, which means when particles spread apart. Okay. Liquids have moderate densities, so they're less dense than a solid, more dense than a gas. They can diffuse, which means they can spread out. They are fluid, which means that they flow. Hopefully you should all know that liquids flow. And they also have a property called viscosity, which is most of you might associate with the word thickness. Okay, so a good example of a very viscous fluid would be something like honey or syrup. It's very thick. Whereas something with a low viscosity or high viscosity, rather high flow rate, would be something like liquid water or oil. It flows very, very easily. And so that those fluids would have a low viscosity because they have a low resistance to flow. Okay, so essentially think about viscosity like thickness. Gases, they expand to fit their container. They are also fluid, just like liquids are. Gases are compressible, which if you understand an internal combustion engine, that's what's happening in your cylinders. The air is being compressed as the piston comes up, forcing that small little explosion, and then the engine runs. So gases are compressible. Gases can also diffuse and effuse. So to diffuse means that gas particles can mix with one another and then spread out. That's why if you spray a perfume, for example, in one corner of the room, eventually everybody in the other corner can smell it because those perfume particles have diffused throughout the air in the room. Effusion is when gas particles pass through a very small opening as they go from an area of high density to an area of low density. Good example here would be if you run over a nail with your car, the gas in your car tire will start to effuse out of that small opening. Or another good example would be a pinhole in a balloon. That gas is going to effuse out of the balloon to the outside as it passes through that small pinhole opening. All right, you guys saw this diagram in the activity that you completed yesterday. I want to go over it a little bit with you now. So this activity is a phase change graph of water specifically. And what you can see here, I want you to look at these two flat portions of the graph. Okay, those two flat portions of this phase change graph or energy diagram of water, those are the places where water's phase is changing. So down here, this is the phase change where water is going from a solid to a liquid, or reverse, from a liquid back to a solid. So it's either melting or freezing. Up here, this flat portion or phase change is when water is going from a liquid to a gas, or reverse, gas to liquid. So it's either boiling or evaporating, or condensing from a gas to a liquid. Okay. Pay attention to how both of these points, when the phase of the substance is changing, energy still increases. Okay, we're still moving to the right energy-wise. However, the temperature remains constant. Okay, so that's kind of a big takeaway that I want you to see here, that as a substance is changing phase, the temperature remains constant because the energy it's gaining is being used to change the phase of the matter, not raise the temperature of that particular substance. Okay, so that's an energy diagram or a phase change graph. You guys saw that yesterday. Some quick phase change vocabulary for you. A lot of these words are words you've seen before, so we're not going to spend a long time, so make sure that you write quickly here. But some vocab associated with the phase change of going from a liquid to a gas, or reverse, gas to liquid. Vaporization. So vaporization is the process of a liquid absorbing energy and becoming a gas. That can occur through boiling, which is where you're adding heat rapidly, or evaporation, which is where it's a slower process where just the surface particles will eventually evaporate. In either case, the substance is vaporizing. It's going from a liquid to a gas. The difference is the rate at which that's happening and whether or not the whole liquid is going from a liquid to a gas or just the surface particles are going from a liquid to gas. The other vocabulary term to pay attention to with the liquid to gas phase change would be the reverse. So when we have a gas losing energy and becoming a liquid, and that's called condensation. You guys see that in the summertime when you've got a cool drink outside. So if you have like a cold can of soda or a cold glass of water, you'll see water form on the outside of that container. And no, that is not the water going through your glass. It's the water vapor in the air losing energy and going from gaseous water to liquid water on the surface of your glass or can. So those are some terms associated with the liquid to gas phase change. Solid to liquid phase change. When you have a liquid that becomes a solid, that's called freezing because that liquid is losing energy or getting energy removed from it so that it loses enough energy to become a solid of whatever substance you're looking at. Melting is the reverse. So melting is when you have a solid substance that you add energy to so that those particles begin to move faster and become a liquid. Now, two phase changes that you may not have heard before, you guys read them in your book, are sublimation and deposition. These two phase changes have to do with going directly from a solid to a gas or a gas to a solid, and you skip the liquid phase. So if you look at the picture on the right, that picture shows you sublimation. That shows you solid carbon dioxide going directly to the gas carbon dioxide because of how quickly the temperature is changing. Okay, that's called sublimation. The reverse of sublimation is called deposition, which is where you have a gas that loses energy fast enough to go directly from a gas to a solid. A great example of that is like on a late fall morning or early spring morning, you can see frost on your windshield, your grass, maybe the trees or the bushes outside. Frost is gaseous water vapor depositing itself quickly and going through deposition. So it's going from a gas phase to a solid phase very quickly on the surfaces of those objects. This diagram is something you guys all saw on that activity that you just corrected. It's a phase diagram. And what I want to draw your attention to particularly about the phase diagram are the axes. Okay, so look very closely at your y-axis here. Okay, so we've got the y-axis is pressure and the x-axis is temperature. Okay, so what this diagram does is it relates the three states of matter, solid, liquid, and gas, to pressure and temperature, because pressure and temperature are the two variables that have the greatest effect on the state of matter of a substance. So if you look at this graph, you can see the effect of increasing the pressure or increasing the temperature on a substance and what phase of matter that particular substance will be at different temperatures and pressures. I've included this phase diagram in your notes because I really like how it shows you where on the graph you can see different phase changes. Okay, so here, as we go from solid to liquid, this shows you melting or the reverse, freezing. Over here, liquid to gas, vaporization or condensation. And then down here, there's that little section where you can see those two new phase changes, sublimation, going from solid to gas, or deposition, going from gas to solid. Okay. Now, there is one point on here I'd like to point out to everybody. Make sure you're watching. It's that little dot right there. That little dot is known as the triple point. And we're going to talk about that here in just a second. So the triple point on a phase diagram is the point at which the pressure and the temperature are just right for that substance. And at that pressure and temperature, that substance can exist in all three states of matter. Okay, so this phase diagram is the phase diagram for water. So the triple point on this phase diagram is the temperature and pressure that ice can coexist with liquid water as well as water vapor. Okay. The other things you can see on a phase diagram are melting point and boiling point. So melting point and boiling point are the temperatures at which a substance will go through those phase changes at 1 atm. So anytime a question were to ask you what is the melting or boiling point of this substance and give you the phase diagram to figure that out, you would need to find the 1 atm pressure on your y-axis. Okay. Quick side note here, atm stands for atmospheres. It's just the unit that we use for pressures. So you'd find 1 atm of pressure and follow that all the way over. And then the point at which 1 atm crosses this solid liquid line here, that's the point that your substance goes from a solid to a liquid. So that point right there is the melting point or freezing point. And then as you continue following that line of 1 atm all the way over, this point right here, where the 1 atm pressure crosses the liquid and gas line, that's where your vaporization or condensation point is on your phase diagram graph. Okay, so it's important that you guys know and understand how to use these and what they show you. So be sure that you're comfortable with those. Okay, you guys all have this phase diagram in your notes and these 7 questions. I'd like you to get together with somebody sitting near you and then answer those 7 questions. Once you've answered those 7 questions, self-check with another group near you to be sure that you all agree on what the correct answers are. And then you guys can either go over the correct answers together today, or we can go over the correct answers together tomorrow. Alrighty? All right, stay tuned for our next episode of Case Chemistry, where we're going to be talking about intermolecular forces. Woohoo! Hit that like button.